We will continue our lecture with evaluating a classifier. We will see what are the techniques that we can tell uh, we are doing a job on building our classifier. For the evaluation, first of all, we are interested to see if the machine predict the label for our class correctly. Then we want to see what is the classification accuracy. Basically, the accuracy, we define it as a percentage of the correct classification. That means we have a test set, and based on the test set, we hide the label of the class. We give this test set to the classifier, and then we will see what is the number of the correct tag, a correct predicted class. For the accuracy, simply the formula is a total test instance classified correctly, the number of the correct class, correct labels uh, over the total number of the test instance that we have. Maybe you are interested to know more about the n-fold cross-validation. It is an evaluating method, but basically we use it in the training phase as well. We evaluate and we train the model. We will see how does it work, the n-fold cross-validation. Usually, when we have the limited annotated data, the annotation of the data is very expensive because we need to uh, manually classify the data for the training purpose. And then we need the human labor to do this classification and add the tags. That is very expensive. Usually we have a limited labeled data. After that, when we want to do the building or classification, we can use these techniques. The techniques is that we can do the several iterations, like the n-fold, n times iteration. In the first iteration, we keep 20% of this label data as a test data and 80% for the training purpose of the classifier. Then we build our, using the modeler, we build our model, and now we can evaluate the classifier over the test data set. In the next iteration, we choose another 20% from this data set and 80% for training. And we train our model, we evaluate. In the same way, we go through the third iteration, fourth iteration until the n. For example, n could be 9-fold cross-validation, or 10 times we train the machine. In this way, you can now see based on which iteration we get the better accuracy. And now we choose that model as the good classifier. The n-fold for the cross-validation is very popular in the machine learning, and I mentioned especially when the label data set is small and we don't have that much of the training data set labeled, we can use this technique. Other technique is the confusion matrix. The confusion matrix, it's this matrix that you can see. We have the actual positive, what is the number of the elements in the test set that are correctly classified. Then we have a true positive. The actual negative, these are the elements that they have the tag of the correct the correct negative. We put it in the true negative. And also we have the misclassification. There are the misclassification as a false positive when are not positive, but falsely they went to the class of the positive, and the false negative when we misclassify them as a false negative. Then Based on this matrix, we can have what is the number for each group, the true positive, positive, false negative, and then true negative. That's a confusion matrix that will tell us a lot about how our classifier is work in a positive way and in the negative way. After that, one of the very popular evaluation technique is the precision and recall. The precision, we look at the number of the correct classified elements as a true positive over the true positive and then false positive. We want to see how many in the total results that we get, how many of them they are correct, correct tag, and that is the precision. In the recall, we look at the true positive over the true positive and the false negative. That means we want to see if we have a list of the expected element, how much of the element that we are expected they predict, they can find in the prediction output of the prediction model. Here we can see in this diagram what is the precision that will tell us how many selected items are relevant, and in the recall that said how many relevant items are selected. There are the other evaluation metrics like F1 score, because sometimes for some application the precision is very important. For some application the recall is important. We don't want to miss the information, then we need to know which one is important, how many elements we find it, and then through them they are exactly correct, or what is the recall over the coverage of the answer. Then F1 score that will give us the combined precision and recall. Then we can see that as a balanced evaluation metric. Receive the operating characteristics curve is a rock curve or the arc rock. And these are the other techniques. We look at the area under the curve. We look at the curve that goes through the more to the false positive or false negative, and we look at the area under this curve. These are the other popular techniques that we have. Other concerns in the classification, as I mentioned in the previous lecture, the explainability of a classifier is very important for some applications, especially the medical or healthcare application. The explainability is important, why the machine is come to that decision. If we can explain it, that will be very helpful for example, some application of the support of decision making, how we come up to this decision using the classification. Other important aspect, cost of the example, when we want to prepare our input, how much money, how much effort, how much human effort that we need to put to the preparing and labeling the data, and then prepare the feature value. These are the other important aspects to consider. Also, when we look at the performance of a classifier, it's sometimes the classification performance varies for the complexity of the task. If it's the simple task of the binary classification, then we expect the higher evaluation for the precision and the recall. If it's a very complex task, then we can afford more errors, especially when we are talking about the high dimensionality. That is, the classification has become really complicated. The high dimensional, it's the when we are dealing with the limited features, like 10 features, 20 features, 100 features, that's fine. We can control it. But sometimes in the more high dimensional data, we are dealing with the 100,000 of the dimensions. And now how our classifier that will work through all these dimensions and build the model, it's affect the performance. Also, other important aspect is the when we should deal with the sparsity of the data. We have for example, in this matrix, you have the features, 1, feature 2, feature 3, feature 4, 5, but there are lots of in the lots of the location, the value is 0, and we have just few non-zero value. Then this matrix, it's very, very sparse. Then there are the different techniques to transform this sparse matrix to the most condensed version of that. For example, we can keep the location and the value. If we are here, we look at the row number 1, 2, 3, and the column 1, 2, 3. We keep the location and the value for this element. Then we don't need to keep the whole big sparse matrix. But the sparsity, it's another problem we should deal with. Then we have the several other aspects to consider. For example, few instances for a complex classification task. If we have the not enough number of the examples with the correct tag for the label, the annotated data when they are small and the task is very complicated. Sometimes we should deal with the missing features. There are lots of the value, for instance, that the value of this feature is missed. The error in attribute value, the wrong entry to our data, the errors in the label, the misclassified examples. Then when the machine they learn from the wrong classification instance. Another important aspect is the unbalanced class. When we have the number of the example in one class, it's much smaller than the number of the example that we have in other class. For example, we have I work on a project on the classification for the as a prediction for the help decision making in the surgery for the healthcare application, and the data that we received, for example, in more than 85% of the case, the surgery, it was okay. And then the class of when we want to predict when the surgery that goes smooth, we had in the 90% of the case, the example that we had, the feature, it was like that. And then we had just a very unbalanced data. We have a much smaller class when this surgery went wrong. And then when we want to do the classification, considering the features, that was a hard job to build a classifier for this complex task. Overfitting, it's when we have a model, we work with the training data, and it adjusts quickly to this training data and works very well on the test data. But when we apply this model to the new test data, the results and then the evaluation result that will be really varied from the other test sets. For example, if you look at the first diagram, we have a training data, and then in this training data, we build a model. The blue line is our model. We have the 80% of our data set as a training data, 20%, for example, as a test data, and then we will see it works fine. But considering that we have some errors in the training data, some red non-target that goes to the class of the target. Now we have the second model. The second model, it looks better. as you can see, the blue line, it's the perfect identification of the elements in the binary class. But when we work on the different test data, as you can see, the performance of this model, it's not working well. And that was overfit to the training data. Then we should be very careful, especially when we deal with the deep learning and our data set is not that much big. The deep learning model that overfit quickly, then we should be avoid this aspect. When we are dealing with the classification, it's good to know the type of the rule that we are doing, which is the induction. The induction, it means we inferring a general rule about the example that we've seen in the past. It is in the contraction of the deduction. Deduction is inferring the things from the logical sequence what is seen in the data. Usually when we are doing the classification task, then this classification it's doing the induction. That means from the different example, we learn and we build a general rules for that. Here you can see better in the deduction, an example, we have it what we saw, we have, for example, a general rule like all birds fly, and we have some specific example like the cardinal, the type of the bird. The cardinal is a bird. And we have this general rule, we have this specific rule, all this information that comes to the a logic sequence as a conclusion. And the logic conclusion in the deduction, that will be the cardinal is a bird that flies. Then it's related this specific to the general, and then this sequence, it becomes the output of the model. But when we are doing the induction, we have so many examples as a specific. For example, the cardinal is a bird that flies. The second one, the robin is a bird that flies. Then we have several examples. We do from this specific what we can learn as the output of the induction model. We have the generalization. We built a rule to generalize what we saw from the specific, what we learn from the specific. And the generalization, that will be all birds fly. When we do the classification, it is the induction. That means from the examples, from the many specific examples, we will learn to build our model through the machine learning. We build our model by choosing a modeler, which is the algorithm, like decision tree, like the logistic regression, like the deep learning. We build our model, and this model now it can, using this generalization, it can go for the prediction of the class. When we are facing a classification task, it's important to know what features to choose. That's important. Feature engineering is the important aspect in the machine learning. We have, for some problems, we could have the 100 or 1,000 of the features. When we are dealing with a high dimensional, that will be 100,000 of the features. Some features we can observe directly, like the example of the cap shape of the mushrooms or the colors. These are the direct observation, but sometimes these features, they are hidden or a latent variable. We can't look at them and observe them directly. The choosing of how we can choose a class is important. The type for a class, we have for example, a binary class, like for the mushroom, is it edible or poisonous? Or should we do the edible, poisonous, and unknown? Then how you choose your classes, that's important when you build your classifier. How many labeled examples do you need? What should be the volume of the training data set that may require a lot of work to prepare and label the input training data sets and use some part of that as a test data set. We should make sure we don't have the contamination. Training data set is separate from the test data set in a clean form. What modeler to choose is another aspect to consider. Which modeler, which algorithm we should choose to find a better answer. And usually what we do, we train several modeler to build our classifier, and using the evaluation techniques, we will see, considering the task, considering our data, and considering the level of the acceptance of our classifier, which modeler is the better, it's a better, build a better model for us. In the classification task for the machine learning, what we learned, we went over the data analysis task, we went over the classification task, how we can build a classifier, and we saw how we can evaluate the classification, the classifier. Then now that was the overview, a simple overview for the classification task. Thank you for your attention.